Hey everyone, welcome back. I'm really excited you're joining me for today's explainer, because we're doing something a little bit different this time. We are going to take a virtual factory tour. Together, we're going to walk through one of the most incredible, massive-scale industrial operations on the planet, the contact process. This is the fascinating chemical process used for the large-scale manufacture of sulfuric acid. It's a substance so vital that a country's industrial strength is actually often measured by just how much of it they produce. And today, we're going to be looking at a video illustrating the whole thing, using a flowchart and animations.
I mean, just look at the massive scale of this industrial plant. It's an absolute labyrinth of pipes, towers, and reaction chambers. It looks totally intimidating, right? But I promise you, by the end of our time together today, you're going to understand exactly what is happening inside these towering metal cylinders. We're going to decode how this complex machinery takes raw, basic elements and completely transforms them into one of the world's most essential and powerful chemicals.
So, here is our roadmap for the tour today. 1. The king of chemicals. 2. Roasting and purifying. 3. The catalytic chamber. 4. The oleum bypass. 5. Pollution control. And 6. Everyday applications.
All right, let's jump right into section 1, the king of chemicals. Okay, let's dive into this. This flowchart you're seeing, it's our definitive map for the contact process. It beautifully illustrates the large-scale manufacture of sulfuric acid. You can see the raw materials coming in on the left and pure concentrated sulfuric acid flowing out on the bottom right. We're going to break this complex schematic down step by step so you can see exactly how the chemistry flows from one chamber to the next. Moving right along to section 2, roasting and purifying. This is stage 1. So the process actually starts off pretty simply. We need sulfur, right? Factories either burn pure sulfur or they roast metal sulfides in the air. This combustion gives us our very first intermediate gas, sulfur 4 oxide. But, well, here's the catch. This gas is dirty, like really dirty. It contains dust particles and a bunch of other impurities from the raw materials. If we let those impurities move forward into the rest of the factory, they'll completely ruin the process. They do what chemical engineers call poisoning the catalyst. So we absolutely have to clean it. First, the gas is passed through an electrostatic precipitator to pull out all the dust. Then it's bubbled through concentrated sulfuric 6 acid to strip away any moisture. That leaves us with a perfectly dry, pure gas.
Which brings us to section 3, the catalytic chamber. Welcome to stage 2.
Now, inside this chamber, we've got to add more oxygen to our sulfur 4 oxide to create sulfur 6 oxide. But this reaction doesn't just happen easily on its own. It really needs a catalyst to speed things up. Now, historically, platinum was considered, and honestly, it's a fantastic catalyst. But here's the secret as to why they don't use it today. Platinum is incredibly expensive. And remember those impurities we just talked about? Platinum is very, very easily poisoned by them. So, the crucial point here is that modern factories almost universally prefer vanadium 5 oxide. It's way cheaper, and it's far more robust against any lingering impurities that might have somehow snuck through our purifiers.
Now, this entire chamber relies on a literal chemical balancing act. To get the absolute maximum amount of sulfur V oxide, the engineers kind of have to play this game of compromise. See, the chemical reaction that forms this gas is exothermic, meaning it releases heat. And according to the rules of chemical equilibrium, if you want more product from an exothermic reaction, you should actually lower the temperature. But if the temperature is too low, the reaction happens at a snail's pace, and the factory would literally go bankrupt waiting for it. So they use a compromise temperature of about 450 degrees Celsius and a pressure of 2 to 3 atmospheres. These are the optimum conditions that provide the perfect sweet spot balance between a high yield of the product and a fast, profitable reaction speed.
And honestly, that compromise works brilliantly. By sticking to those specific optimum conditions and using that vanadium 5 oxide catalyst, the factory achieves an absolutely staggering 98% conversion rate of sulfur 4 oxide into sulfur 6 oxide. It is a total triumph of industrial chemistry.
All right, let's head into section 4, the oleum bypass. This is stage 3.
So, we've got our sulfur V oxide gas, and we know that sulfuric acid is basically just this gas combined with water. So, I have a logical question for you. Why don't the engineers just pipe this gas directly into a giant tank of water? I mean, it seems so simple, right? Well, simply put, if they did that, it would be a total disaster. The reaction between sulfur V oxide and water is incredibly exothermic. We're talking an immense amount of sudden heat. That heat instantly boils the newly formed acid, vaporizing it into this thick, highly corrosive, and incredibly dangerous mist of fine sulfuric acid droplets. That mist would just float right out of the factory chimneys. It's way too violent to control. So the engineers had to invent a pretty clever workaround.
Now, what's really interesting about this is how beautifully counterintuitive the solution is. Instead of dissolving the gas in water, they actually dissolve the gas into already existing concentrated sulfuric acid. As you can see right here in this equation, sulfur VI gas plus liquid sulfuric acid yields a brand new compound, H2S2O7. This process completely absorbs the gas without any of that violent mist-producing explosion.
So that new compound, H2S2O7, is called oleum. It's this really thick, heavy, oily liquid. You can kind of think of oleum as an intermediate step. It's the ultimate safety compromise. We're essentially trapping that reactive gas inside an acid cage, keeping the whole factory safe from that deadly mist. All right, so once the oleum is safely formed, we can finally finish the job. The factory takes this thick oleum, pumps it into a circulating tank, and very carefully and safely dilutes it with liquid water. Because the gas is already bound up tight inside the oleum, adding water now is entirely manageable. The water breaks the oleum down, and out flows our final, beautiful product. Massive quantities of 98.5% concentrated sulfuric acid, ready to be cooled down and shipped out. Now for Section 5, Pollution Control. Let's talk environmental impact. So remember a minute ago when I said the conversion rate in the catalytic chamber was 98%? Well, doing the math, that means 2% of that sulfur IV oxide gas doesn't react. And if that unreacted gas escapes out into the atmosphere, it becomes a major pollutant. It can cause devastating acid rain and respiratory illnesses in any surrounding communities. To stop this from happening, factories use a process called scrubbing. Before those exhaust gases are ever released from the chimney, they get passed through filters lined with strong alkalis, like calcium hydroxide. The toxic sulfur IV oxide reacts with the calcium hydroxide to form a solid, completely harmless calcium sulfite and water. It's an absolutely vital chemical safeguard to protect the environment. Finally, Section 6, Everyday Applications. Let's look at the uses of sulfuric acid. And this brilliantly illustrates exactly why we care. Sulfuric acid is literally the silent engine of modern life. Once it leaves this plant, it goes into manufacturing the fertilizers that literally grow the food on your table. It's used in the detergents that wash your clothes. It is the actual electrolyte acid inside the battery that starts your car every single morning. It's in paints, plastics, processing metal ores. Honestly, almost every manufactured product you touch has at some point relied on the sulfuric acid produced by this exact contact process. Which brings us to the end of our virtual factory tour. The contact process is, honestly, a masterclass in human engineering. It takes raw earth and turns it into the very building blocks of modern civilization. But it also requires constant vigilance to make sure we don't destroy the environment in the process. So, I'll leave you with this to ponder. As our need for these vital chemicals grows, how do we continue to balance vital industrial progress with our crucial responsibility of environmental stewardship? Thank you so much for exploring this with me today, and as always, keep learning.